In this videos we're going to talk about our concentration cells. A voltaic cell can function with the same species at the anode and cathode. Now if you look at your reduction potential, your voltage, you're going to get 0. But the E can be positive if the concentration of the anode is less than the concentration of the anode. So remember that cells that only generate voltage due to differences in concentration are called concentration cells. Okay, so when the concentration at the anode equals the concentration at the cathode, your E equals 0, the system is at equilibrium. And when the system is at equilibrium, it's dead. Your cell is dead. So here the reaction is going to proceed. The concentration at the anode is going to increase, and the concentration at the cathode is going to decrease. And then your E is going to equal 0. So here's what a concentration cell would look like. We have nickel at the anode and at the cathode. We have a higher concentration of reactants. This causes the forward reaction rate to be greater than the reverse reaction rate. The system reaches equilibrium when the concentrations are equal. So at that point, your E is equal to 0. Redox reactions are always at equilibrium when E equals 0. So an electrolytic cell is one where you have a non-spontaneous redox reaction. It's going to require a source of direct electrical current hooked up to 2 electrodes. Those electrodes are going to be immersed in a molten salt or an electrolytic solution. Your anode is going to take electrons from one species in the solution, remember that's oxidation, and the cathode is going to give electrons to another species in solution. This is your reduction. So the source of electric current is going to be what drives this reaction. Okay, it's not spontaneous, so electrical energy has to be added to drive this reaction. So here's an electrolysis of molten sodium chloride. So the anode is going to pick up the electrons in an electrolytic cell. In this case, your molten sodium chloride, your chloride is oxidized because it's the only element that's willing to give up electrons. So it gives up electrons and forms chlorine gas, which bubbles out of solution. The electrons that were given up by chloride flow through the wire to the battery, where they reduce the cation in the battery's cathode. For this cell, the anode can easily be identified because you'd be able to see the bubbles. Electrons are evolved from the solid metal in the anode of the battery as it becomes aqueous. These electrons flow to the cathode in the molten sodium chloride. The sodium ions pick up these electrons to become neutral sodium atoms because they're the only species present that are willing to pick up the electrons. This type of reaction does not require a salt bridge here. Now, when we're dealing with an aqueous solution, we have different species that may be oxidized or reduced, like water or an ion. You may also have a solution with 2 different salts mixed in water. In these cases, you would have 3 possible oxidations and 3 possible reductions to choose from. To determine what's going to be oxidized and what will be reduced, you have to look at the standard reduction potentials for each species present. So reduction at the cathode, you have all positive ions and water available for reduction. The most positive or the least negative reduction potential represents the largest decrease in potential energy for the electron. Oxidation at the anode, you have all negative ions and water are available for oxidation. The most positive oxidation potential will be favored at the anode because this is where your oxidation takes place. Your table of standard reduction potentials only provides you with the reduction potentials, so remember to change the sign to make them oxidation potentials. The oxidation potential for iodide is negative 0.53 volts. So we change that to a positive 0.53 to look at oxidation. So negative 0.53 volts is the least negative or the most positive, which means that ion would be oxidized at the cathode. So in this cell, your iodine solid is produced at the anode, and the hydrogen gas and hydroxide are produced at the cathode. The anode and cathode could be easily identified because you could see the solids and the bubbles. The pH at the cathode would also be increasing due to the formation of hydroxide ions. This type of thing could easily be identified by adding a few drops of an acid-base indicator to the solution. Now, if we look at an example here, we've got a direct current applied to aqueous copper 2 bromide solution. So we want to determine the reduction half reaction, the oxidation half reaction, the overall reaction, and delta G. So we have to look at our reduction potentials for each of our electrolysis reactions here. So if we look at our reduction values for water and all positive ions, we see that we have negative 0.83 for our water, and we have positive 0.34 for our copper. So which reaction has the most positive or the least negative reduction potential? That's going to be our copper with the most positive value. So then we look at our negative ions in relation to our water. So which reaction is going to have the most positive or the least negative oxidation value? Remember to change the sign of your reduction values to oxidation. So that's going to be your bromide ion that has the least negative value. So we do write our overall reaction, we do have to make sure that our electrons cancel. So you may have to multiply to make sure that they cancel. And make sure that your reaction will balance overall. So make sure you have a coefficient of 2 on your bromide ion to balance out your bromine gas. And then finally, we want to calculate our delta G value. So the first step is to find our reduction potential, our voltage. So we use our E values, and we plug in our numbers that we had on our previous slides, and we get a negative cell potential, negative 0.73. So this means that our reaction is not spontaneous. And because your electrolytic processes are not spontaneous, electrical energy has to be supplied to drive the reactions. Then we can find delta G once we know our E value. So we plug in our values. We had 2 moles of electrons that came from our redox reaction. Faraday's constant, 96,500 coulombs per mole. And then multiply by our E value. Remember that delta G is always given in kilojoules per mole. Okay, and remember that your delta G is going to be positive for these reactions because they are non-spontaneous.